Okay, Matt Roscoe here at the University of Montana with a short introduction to Chapter 4, the Alexandrian School in Euclid in our History of Math course. So lots to go on here. So we'll try to get through the first three bullets in this, this first introductory lecture. But an overview of the chapter, there's a discussion of the importance of Alexandria as a center for learning in ancient Greece. Then there's a discussion of Euclid's elements and its importance to our science. And then there is kind of a general overview of the book of the elements. There's book 1, elementary plane geometry, 2, geometric algebra, circles and their properties in book 3, constructions in book 4. And then books 5 through 10 have kind of a variety of topics, ratio, proportion, and some number theory. Books 11 through 13 deal with spatial geometry, so three-dimensional geometry. The end of the chapter does a little bit of work on two other important mathematical figures from around the time of Euclid, who came after Euclid, I should say, Aristophanes and Archimedes. So let's talk first about Alexandria. Founded by Alexander the Great in 323 BC, the city of Alexandria served as the center for Hellenistic culture for 1,000 years. And the center of learning in Alexandria was the so-called museum, which was the forerunner to the modern university. I will say there's just an excellent episode of Cosmos, Carl Sagan's Cosmos, and it's actually episode 1. Now, I will say this is a somewhat old series that was sort of redone recently, but the old series is now available on YouTube, and I've given you the a link here to the or I guess there is a link in the slides to the actual video from the Cosmos episode, and it's in around I guess minute 38 where we see Carl Sagan discuss a bit of this, and I thought it'd be fun to watch a bit of it, so just a couple minutes here.
All that survives is this dank and forgotten cellar. It's in the library annex, the Serapeum, which was once a temple, but was later reconsecrated to knowledge. These few moldering shelves, probably once in a basement storage room, are its only physical remains. But this place was once the brain and glory of the greatest city on the planet Earth. If I could travel back into time, this is the place I would visit. The Library of Alexandria at its height 2,000 years ago. Here, in an important sense, began the intellectual adventure which has led us into space. All the knowledge in the ancient world was once within these marble walls. In the Great Hall, there may have been a mural of Alexander with the crook and flail and ceremonial headdress of the pharaohs of ancient Egypt. This library was a citadel of human consciousness, a beacon on our journey to the stars.
So I hope that at least gets you interested. I think it's a wonderful program, if a bit dated in a way it's viewed, but no less dramatic than it was in the late 70s when it was first released. I'd really encourage you to take a look at it. It would give you a better appreciation for the importance of, I guess, the Museum of Alexandria. So before the museum's destruction in AD 641, it produced many of the distinguished scholars who would shape the course of mathematics during their lifetime and well into their future. So chief among these would be Euclid, but also important were Archimedes, Aristophanes, Apollonius, Pappus, Claudius Ptolemy, and Diophantus. So among the mathematicians of Alexandria, one stands apart, and that is Euclid, who is around 300 BC. The reason Euclid is so influential is because Euclid is the author of the Elements, which is the world's second most widely circulated book in the history of the world. For 20 centuries, it was the textbook for mathematics. And since its first printing in 1482, there's been over 1,000 editions. So you should know a little bit about Euclid's Elements and how Euclid sort of begins the heavy lifting of building up mathematics. He assumes 5 postulates in his founding of the Elements. The first one is that a straight line can be drawn from any point to any other point. So thus the idea of an unmarked a straight edge. A finite straight line can be produced continuously in a line. So that means if we have a segment, we can continue it on and make it into, say, a ray or into a full-fledged two-dimensional line. And then it says that a circle may be described with any center and any distance. So we have a circle drawer that, given a point and some distance, that we can draw any circle. And then all right angles are equal to one another, so the idea that if we have a right angle in one area of the drawing and another right angle in another area of the drawing, then those two right angles are going to be equal in measure. And lastly, if a straight line falling on two straight lines makes the interior angle on the same side less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. So this is by far and away the one that is most curious of the 5 elements. And maybe we should take a quick moment just to think about what it's saying here. So let me pull this up. So we have 2 lines, let's say. And it says if a straight line falls on any 2 lines, such as this, then let's go back and read it again here. And it makes interior angles on the same side less than 2 right angles, then the 2 straight lines, if produced indefinitely, meet on that side. So let's go to that. Back here. So if we have a straight line falling on 2 straight lines and the interior angles formed, so there are 2 interior angles formed on either side of the red line. I guess there is 1 and 2 on this side and 3 and 4 on this side. And I guess what it's saying is that the side of the line where the 2 interior angles formed sum to something less than 2 right angles, less than 180. Then that's the side that these 2 lines are going to meet. So let's just assume that angle 1 plus angle 2 is less than 180 degrees. Therefore, I guess let's call this one M and this one N. So therefore, M and M meet on the left. I guess, what do I mean by that? Left of this line, let's call it L. So I guess what we're really saying is that somewhere out here there's got to be a spot, right, where these 2 lines are going to meet if they were produced indefinitely. So that's the idea of the 5th postulate. And the 5th postulate, of course, is called the parallel postulate because the idea is that our notion of parallelness flows from that 5th postulate, at least parallelness in the plane. There are also 5 common notions, things that are added, things that are equal to the same thing are also equal to each other. We sometimes think of that as transitivity. If equals are added to equals, then the wholes are equal. So we can take things that are 2 equations and combine them into one. If A is equal to B and C is equal to D, then A plus B is equal to C plus D, that sort of thing. If equals are subtracted from equals, their remainders are equal, so same statement as number 2 except for in subtraction. Things that coincide with one another are equal to one another. In other words, if things are coincident, then they are equal. And the last thing is the whole is greater than the part. So 5 common notions. So literally from these 5 postulates and these 5 common notions, Euclid builds up a gigantic number of logical necessities that today we would think of as modern, or I should say traditional, Euclidean geometry. And by Euclidean, what we mean is geometry in the plane, so in two-dimensional sense. So among the postulates and common notions, one deserves special mention. That's the 5th postulate, sometimes called the parallel postulate. And the special thing about the parallel postulate is that it took us almost 2,000 years, but we eventually realized that postulate was sort of an optional one. It's one that was particular to the geometry of 2 dimensions, two-dimensional planes, and that it could be replaced with different notions. For example, if geometry was taken off the plane and put someplace else, for example, on a sphere. So if you can think about, travel on the planet, on the surface of a sphere, what is a straight line there? What does it mean to be parallel there? Those things kind of change when we're in a different setting other than planar two-dimensional geometry. So, and of course, it was the 5th postulate that was the struggle for mathematicians when geometry sort of outgrew 2 dimensions. So we should probably do a few of these propositions that are in Euclid's elements. So let's take a look at proposition number 5. Each one of the proofs or statements are offered as a proposition, and then proof is provided for each one of those. So in proposition 5, we have an isosceles triangle, and the angles at the base are congruent to one another. Okay, so let's switch over now to desktop view and think about, take a look at how Euclid proved this particular proposition. So proposition 5, we think that the base angles of an isosceles triangle are congruent. So the definition of an isosceles triangle, of course, is a triangle with 2 sides congruent. So we'll start with that. This is sort of a picture. So we'll say this is triangle A, B, C. We're going to say this side and this side are congruent. So the way that two base angles of any isosceles triangle are congruent. So let's see, his argument is something like this. Number 1, he says, go ahead and construct AB and AC as rays. Okay, so we're going to do that. Construct this and this, sort of extend them. Okay. Okay, so why can we do that? Well, this turns out to be postulate number 1. So in other words, we can take any finite segment and extend it indefinitely. Okay. Number 2, what we're going to do is construct points I'm going to call them F and G such that AF equals AG. And this would be a common notion 2. So how could you do that? I mean, if you want a point F and G such that AF and AG are the same, well, you could just set your compass and inscribe a circle, for example, right? So AF and AG are the same here, so I'll call this one point F and this one point G. Common notion 2 allows us to do that. So, I mean, this is the same distance as that if they're coincident. Let's see. So number 3. He says number 3 then that triangle FAC is going to be congruent to triangle GAB, and that's by side angle side triangle congruence, which turns out to be one of the propositions that precedes 5. It's proposition 4. So let's just think of that. AFC. So AFC, I mean, we would have sort of that AFC, and AGB, or I think I have it. Oh, I see. So it's FAC, and so it would be GAB. Yep. And the claim there is by side angle side. Well, I guess I can get that, right? Because in FAC I have FA, which is congruent to GA, right? So this side is congruent to that side. And then let's see, by definition, AC is going to be congruent to AB because of the fact that we have, so those are the two sides. And then the angle that's contained in between them is angle A, which is common to both. So side angle side seems like a valid argument. So number 4, what can we conclude? So we can conclude then that FC is equal to GB. We can conclude that angle ACF is going to be congruent to angle ABG, and angle, let's see, AFC is going to be congruent to angle AGB. So what FC, so this distance here, I don't know, I'm going to kind of put a 1, 2, 3 on it if that's all right. It's got to be congruent to this distance here. So that's this statement. ACF, so this whole angle here, right, has to be congruent then to this whole angle here. ACF, ABG. And then let's see, AFC, so this whole angle here has got to be congruent to this whole angle here. Okay, so let's see, and this is all by what we would call today corresponding parts of congruent triangles are congruent. But in a sense, you know, once you have the congruent triangles up here, this is just common notion 4. So common notion 4. If two things are congruent, then their parts are congruent. And let's see, so on to number 5. At number 5, what we get in Euclid's proof is then that the triangle BFC has got to be congruent to the triangle CGB. So let's see, BFC, so it's this little guy in here has got to be congruent to CGB, so it's sort of this slicing triangle in here, right? And they say that's by side angle side. So that's again prop 4. And let's just make sure that we understand. Well, it looks like BFC CGB. So I think the idea here is that since this distance, well, we certainly have this distance and this distance to be the same, right? So that's, and certainly this side is this, or this angle is the same in between, but we don't have that BF and CG are the same. But I guess that must be assumed in the proof to be the same, or not assumed, but logically to be the same, because if this distance is equal to this distance, because that's the way we constructed it, and this distance and this distance is equal because it's an isosceles triangle to begin with, then the leftover must be equal. So interestingly, Euclid kind of skips that step, waves his hand at it, but certainly that segment and that segment could be shown in, say, step 4.5 through a subtraction argument. So we get that these two little triangles are congruent in the figure. And so from there, where Euclid goes next is to say then that angle BCF has to be congruent to angle CBG, and that's by again this side angle side, the common notion 4. If the triangles are congruent, then their parts are all congruent. Sometimes we think of this as CPCTC, corresponding parts of congruent triangles are congruent. CPCTC. So let's mark that off. So what is that? That's this little angle in here, BCF. BCF is this little angle right in here. And CBG is this little angle right in here. And remember, what we're after is we're after these two base angles being congruent. And I think now you can see it. We have this whole angle congruent to this whole angle. We have this little angle congruent to this little angle. So if I just take those two little angles away from the big angle, what is left is the base angle of the triangle itself. So let's make that last argument. So number 7. Here we would have that angle ABC then is equal to ABG minus angle CBG, and this is common notion 3. I'll just call it CN3, and that's equal to angle ACF minus angle BCF. So let's see, we did ABC is equal to ABG minus the CBG. Okay, but the CBG is the congruent to this one, to the the ABG is congruent to ACF. So we subtract, we I guess substitute there, and CBG is equal to BCF. So that's from line 6. So that's common notion 1 equals, can be substituted. And let's see, so lastly, we know that ACF, take away BCF, is going to be just ACB. And that one would be common notion 1 again. And so what we've shown then is that these base angles, ABC and ACB, are congruent as desired. And so quite an involved proof. One of the things you might notice is that it seems really hard, to do. But one of the things that you might appreciate is that this is proposition 5 of the book, right? It's only the 5th thing that Euclid has constructed. And so he has very little to rely on to build this up at this point, because there isn't a lot of machinery that precedes it. In fact, the one big thing that he needed that you can see that precedes it is side angle side triangle congruence. So really an elementary, I guess, geometric idea. Base angles of an isosceles triangle are congruent. But it takes some pretty heavy logical lifting to do it with so few tools. So I hope you can appreciate that a bit. Let's try another one. If one of the sides of a triangle is produced, then the exterior angle is greater than either opposite interior angle. So this is proposition 16. It's about sides of triangles and exterior angles. So let's go ahead and try this one. Proposition 16. Um, so here we go. Let's give it a shot. We'll start with a triangle. And we'll go ahead and extend, a side so that we get an exterior angle. Okay, so let's call this ABC. And we'll extend this. So I guess number 1, extend BC and construct point, let's say D on BC. And I suppose I should probably say exterior to the triangle. Let's see. Then it says number 2. So this, of course, I'll not. The extension is one of the postulates. Then we're going to construct the midpoint of AC. So the construction of the midpoint must be somewhere I mean, we don't have that as one of the postulates, so it must be one of the propositions that precedes 16. So let's just assume we can do it, and we'll construct the midpoint of AC, and we'll call it E. And so if we've got a midpoint, these two segments are the same. And then number 3, he says extend BE. Call this E. Such that BE equals EF. So what am I going to do? I'm going to extend BE such that BE equals EF. So I guess I could just kind of try to keep this fairly accurate. BE equals EF. So somewhere out here we have an F. And this distance and this distance are the same, right? So what would he say at this point? At this point he says angle AEB is going to be then congruent to angle FEC. And this is by proposition 15, the one that precedes this. So let's see, AEB has got to be the same thing as FEC. So which angles are we talking about here? I guess these are angles, I don't know, let's call them this angle and this angle. So what we call now vertical angles. So proposition 15 must be a vertical angle proposition. Number 5, then he says that triangle AEB is going to be congruent to triangle FEC, and that's by side angle side, which is proposition 4. Let's see, so AEB has got to be the same thing as FEC, and it's interesting he doesn't really draw in the segment FEC, but I guess we could draw it in and think about it. These two triangles are the ones that he's claiming are congruent. Side angle side, I can see it there, yep. Let's see, so number 6 then, angle BAE has got to be then congruent to angle FEC, or FCE. And here we could call this common notion 4, but we'll use the modern notation CPCTC. So BAE, where does it BAE? So this angle up here, I don't know, let's give it 2 lines. It's got to be the same as FCE, this angle down here, and that's by corresponding parts of the congruent triangles are congruent. Okay. And then number 7, he says that angle, let's see, DCA has got to be greater than angle FCE. And this is common notion 5. So let's see, DCA, right, this one right here, has to be greater than FCE. Okay, yeah, I agree. DCA is made up of part of it is made up of FCE, so the whole is greater than the sum of its parts, or the whole is greater than any of its parts. So I would agree with that. So now he says combine 6 and 7. We get what? We get angle DCA is greater than 6 says that these two are the same, so FCE is the same as BAE. Which is just what? That angle DCA is greater than angle, let's see, instead of BAE, it's the same thing as BAC, right? So what have we shown? We've shown that DCA, this exterior angle out here, right, has got to be greater than BAC, that remote interior angle. So this one exterior angle to the triangle is certainly greater than A. And we could just say by a similar argument, we could prove it to be true for the angle at B. Instead of bisecting AC, we'd have to bisect AB and construct the figure the other way. But by a similar argument, we could show that angle DCA is greater than the angle at ABC. So quite a bit of I guess, logic going into the argument that the exterior angle of a triangle is always greater than either of its two remote interior angles. Yeah, I guess again, we're fairly early in the book. Proposition 16. There are only 15 propositions on which to rely on. He does rely on 2 of them, 15 and 4, and then quite a bit of the postulates and common notions to make this argument. So I think with that we'll pick up from there when I get back on Wednesday, and I look forward to seeing you all then.